Okay, dear students, good day. This is Dr. David Pokrajak. Today I will essentially try to finish our lecture from last Monday, which I couldn't finish because I was sick on Wednesday. And this lecture is on hidden Markov chains. And more specifically, what I will discuss here is so-called the Viterbi algorithm. I will remind you on an example which I gave last time, which is basically an example, hypothetical example of a family which moves from Mexico to the United States and back. And we observe whether the family each year was rich or poor, and we are trying to determine the most likely sequence of the movement of the family from Mexico to the United States. And this model can be described by a graph, which I will show now. So basically the graph has two nodes, one representing United States, one representing Mexico. If a family 1 year was in United States, the probability that the family will stay in the United States in the next year is 0.7 or 70%. If the family was in the United States this year, the probability the family will go to Mexico next year is 0.3. If the family was in Mexico, it will stay in Mexico with probability 0.5. And if the family was in Mexico, they may move to the United States with probability 0.5. So this is what we shown last time. And also we talked about the probabilities the family will be rich or will be poor if they are in the United States or if they are in Mexico. So if I recall right, the probability is, if the family is in the United States, the probability the family is rich is 0.4. The probability the family is poor if the family is in the United States is 0.6. The probability the family is rich if the family is in Mexico is say 0.1, and the probability is poor if it is in Mexico will be consequently 0.9. Observe the sum of these two is 1 as well as the sum of these two, because the family is either rich or poor if they are in the United States, or it can be either rich or poor if it's in Mexico. So this is what we know, and we can also assume that we know that at the beginning the family was in Mexico. This we write this way: probability that the family was in Mexico initially was 1, and the probability the family was initially in the United States was 0. Again, the family is either in Mexico and United States. We have only two states, so correspondingly the sum of these two probabilities must be equal to 1. In more general case, if we had more than two states, the sum of the probabilities, these are initial probabilities, the sum of these initial probabilities will be always 1. So this is what we know. What we also assume is that the family was, in consequent years, the family was poor, rich, poor, and rich. So this was, we call these observed alphabet. This is what we observed sequence. And we can denote this observed sequence with O1, O2, O3, O4, O5, and O6. The index here from 1 to 6 indicates the year when we actually observe this sequence. So this is my observed sequence. So this is what is given. This is what is given. And of course, in any interesting problem or algorithm, in addition to what is given, we always have to find something, right? So what we need to find? What we need to find here? We know that at the beginning, observe, probability the family was in Mexico is 1. At the beginning, family was in Mexico. So I can say what does it mean? At time 1, at the beginning, the family was in this state. So the first state at time 1 was Mexico. So this is the state at time 1. Question is, what are, and I can call this also Q1. And now the family may have stayed in Mexico or may have moved to the United States. We don't know. So we know, however, that there must be some state Q2 at year 2. So in year 2 the family was either in Mexico or in the United States, but we don't know where. Similarly, in year 3 the family was in state Q3, and finally last year, the 6th year, the family was in state Q6. So there is change of these states from the 1st to 2nd and ultimately to the 6th year, which resulted with this observed sequence. Question is to find most likely sequence of states that led to the observed output. And when I say most likely sequence of states, how many potential sequence of states are? So one potential sequence would be what this sequence tells us. This sequence tells us that basically family, we know the family was in Mexico in the 1st year, but then the family did not change the state and was always in Mexico. So this is the first possible sequence. And of course, the next possible sequence would be Mexico, 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 US. So this means the family stayed in Mexico for 1, 2, 3, 4, 5 years, and then the family moved to the United States. And the last sequence would be remember the family must always first be in Mexico, because the initial probability of Mexico is 1. So the last sequence would be Mexico, US, 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 US. This will be the last sequence, last possible sequence. How many possible sequences? Well, on each place from 2 to 6, there are two possibilities, either Mexico or United States. So the total number of sequences would be 2 to the 5 or 32. Okay, but that's not of major issue. Obviously, it should be obvious that not all of these sequences are equiprobable. Why? First, if we are in the United States, there is higher likelihood will we stay in the United States than we will go back to Mexico. So a sequence which will contain 2 US in a row will be more likely than a sequence when we switch from US to Mexico. Second, if person were rich, it's more likely the person was in the United States than in Mexico. Why? Because if the person was in the United States, probability the person will be rich will be 40%, while the same probability if the person or the family is in Mexico would be only 10%. So if the family were rich, it's higher. There is higher likelihood that the family was in the United States. These are two arguments which should justify why not all the sequences are equiprobable. And again, what is our goal? Our goal is to start from the output sequence, which is known, and knowing all the parameters of Markov chain, so knowing all the parameters of the Markov chain and knowing the observed sequence, the goal here is to find the most likely sequence of the states that led to the observed output. So how are we going to do that? In fact, I need to introduce a couple of more symbols, simply to simplify the description of the algorithm. So I will introduce the following symbols. Aij. Aij is of course a probability. Which probability? Probability that we transition from state I to state J. And of course, due to this notation I and J, you can envision that there is a matrix A, or we can say set A, consisting of all possible elements I and J. I goes from 1 to n, where n is the total number of states, and J also goes from 1 to n. In our case, how many states do we have? We have 2 states, US and Mexico. So in our case, n is equal 2. Easy. And then our probabilities Aij are A, Mexico, Mexico, which is basically what? 0.5. A, Mexico, US, which is 0.5. A, US, US, which is what? 0.7. Probability that we will stay in US the next year. And of course we have A, US, Mexico, which is probability that from US next year we will go back to Mexico. It is 0.3. So these are our A's. And to formalize further, I also need to introduce a symbol which I call bj of k. What is bj of k? Probability that we generate at the output kth symbol, assuming we are in state j. So we can immediately form what are b, j, k in our case. What are output symbols? Okay, I can introduce set of output symbols. Set of m output symbols. In our case, I can say that V1 is rich, that V2 is poor. So there are two possible outputs, rich or poor. And we basically generate these outputs here, as we can see. Here are the outputs. Here are the outputs that we generate, rich, poor, and so on. So, what are the probabilities? B1 of 1, this is probability of, we generate the kth, the first output symbol, output 1, probability of generating output 1 if we are in state 1. So we are in state 1 and we are generating an output symbol 1. So, translation. What is output 1? Output 1 is rich. State 1 is by this definition Mexico. So with this symbol, B11 is the same as probability rich in Mexico. Why rich and why Mexico? Because Mexico is state 1 and rich is output 1. So the probability somebody is rich in Mexico is what? It's 0.1. What is B1, 2? This index is the index of state. This is the index of output. So this is probability of state 1 generating output 2. Translation. This is probability. State 1 is being Mexico, right? Output 2, well, since output 1 was rich, output 2 was poor. So the probability of being in Mexico and poor is 0.9. We need to redefine also B21 and B22. The first index denotes the state. The first index denotes the state. So what is state here? It's the second state. The first state was Mexico here, so the probability, we are looking at the output probabilities if the state is US. 1 and 2 denote outputs. So this is the probability if the state is 2, US, and the output is 1, which means rich. So this is probability of rich in US, and this probability of rich in US is 0.4. And finally, without further ado, the last probability is probability of poor in US, which is 0.6. So these are our probabilities. B, we already defined a matrix, and we know pi's, probabilities pi's, so I can put all of this concisely. I can write pi of I is 1, pi of 2 is 0. Initial state, if we are in Mexico, probability of initial state is 1, otherwise is 0. I can write concisely B11 is equal 0.1, B12 is 0.9, B21 is 0.4, and B22 is 0.6. And I can write my matrix A, which consists of A11, A12, A21, and A22. I can write my A as Mexico is state 1, US is state 2, zero 5, 0 5, 0 3, 0 7. Zero 0.3 is the probability that from US state 2 we go next year to state 1, Mexico. 0.7 is probability that we stay in US, and 0.5 are the probabilities that if we are in Mexico, here we stay in Mexico, and here we go to US. So here are our probabilities, and now we shall be able to start developing the algorithm. Well, it follows I need one more symbol here. Whoops. We are really killing ourselves with symbols, but it is like it is. So the symbol I need is delta T of I. Ugh. Greek letters. So what is delta T of I? So basically we start from the first time equal 1, and then time equal 2, and time equal 3. So T indicates time in the sequence. Time in the sequence. It follows that I indicates a state. So what this probability could be? This probability in essence is probability that we reached a specific state I sorry, mistake. This is not proper definition of this. So what's delta t of I? Obviously, there is some transition of the states that would lead to a state I after t time instance. So this delta t of I is the probability of the most likely sequence of states that generated outputs O1, O2, OT and led to state QI. Sounds very abstract, so let's try to give an example. Say t is equal 3. What are the observed outputs O1, O2, OT? T is 3, so we are looking at O1, O2, and O3. What are our outputs? They are O1 being poor, O2 being poor, and O3 being rich. So sequence O1, O2, O3 is equal poor, poor, rich. Say I is equal 2. This denotes the state 2. Remember, the state 1 was Mexico, state 2 was US. So I equal 2 indicates that we are in state 2 US at time t equal 3. What would be delta 3 of 2? Delta 3 of 2 is in essence the most likely sequence of moving the parents, the family, from Mexico to the United States, which resulted in the observed sequence of poor, poor, rich, if the family ended up in the United States in the year 3. This is most likely sequence of residence, if you will. That leads to the family being in US. US corresponds to the state 2 at time 3. This index obviously corresponds to the time. So somebody may ask, in this particular case, what's delta 6 of 2? Observe, now this index is 6. 6 means time is 6. So this would be what? The most likely sequence of resonance that leads to the family being where? In the United States, state 2, after the 6th year. So the state is 2, indicating United States, and time is 6. Similarly, delta 6 of 1 would be the most likely sequence that led the family, actually this is the probability of the most likely sequence. So deltas are probabilities of the most likely sequence. Delta 6 of 1 is the probability of the most likely sequence that led the family being where? Index 1 indicates Mexico at time 6. So let's assume that we know delta 6 of 1 and delta 6 of 2. Delta 6 of 1 is the probability of the most likely sequence of events which led to the family to be in Mexico. This is the most likely sequence of events which led family being in United States. We really don't know where is family at time 6, but we will look at these two probabilities and say, if the probability of the most likely sequence of events that led family being in United States index 2 is larger than the probability of the most likely sequence of events that led family being to Mexico index 1. If this is true, then most likely family ended up where? Where in the state where this probability is higher. So, which means in the state 2, and 2 indicates United States. So, if the opposite is true, family most likely ended up in Mexico. This is very important observation, because ultimately we're going to calculate this probability and this probability, and based on these two probabilities we will find out where most likely family ended up. I will now write the algorithm, and then we will try to go through the algorithm, and ultimately I may try to explain why the algorithm works. So this is the Viterbi algorithm. First I need to initialize delta 1 of I. Delta 1 of I is what? That's the probability of the most likely sequence leading our system in the state I at time 1. This probability is equal to what does this mean? What does this really mean? Pi of I is the probability that initially we are in state I. So we are in state I, and then having observed the output 1, observe that the index here is 1, we generated the output 1, which is observed. We know it is generated. So this is the probability the output 1 is generated if we are in state I. So this would be equal to the most likely probability that the symbol O1 is generated if we ended up after the first round, right? We ended up in the state I. So this is basically the initialization of the algorithm. And then we have the following loop. We have a counter which goes from 2 to t minus 1. I did not define t. I shall define t. T is 6, total number of symbols. Generated. Observe we generated O1, O2, O6. So this is the length of the sequence. So T is the length of the sequence. T is the length of the sequence, right? So now basically, as you can see, we have this for loop. And in this for loop, I do the following. So, what I am doing really here, delta t of j is the most likely, the probability of the most likely sequence that led us to state j at time t. And AJI is the probability that we transition from J to I. So what this would be, this is the probability that we were in state J at time T and then transitioned to state I. In other words, this is the probability we reached state I in t plus 1 through state J. Naturally, we don't necessarily know through which state we reached the state I at time t plus 1. We don't know through which one we reached it, but what's logical? Based on the available data, we will find out through which state we most likely reached the state I. How we will find through which state j we most likely reach the state I? We will calculate the product of these two probabilities, and then we will find the maximal value of this product. And precisely that maximal value will be here. So this is most likely, this is the probability that most likely we reached state I. And what is j? That j which maximizes this value would be the most likely state through which we reach the state I. So again, this maximum here of this expression provides the probability essentially of the most likely sequence of states through which we reach the state I in time t plus 1. And what is this? This is the probability that once we are in state j, sorry, this is I, while this is the probability that once we are in state I, we generated the observed output symbol at time t plus 1. So at time t plus 1, we generated an output symbol ot plus 1, and this is the probability that that symbol was generated if we are in state I. So, to summarize, this is the probability essentially, the highest. This is the probability we reach state I, and this is the probability we have output ot plus 1 once in state I. So ultimately, when we multiply these two probabilities, we actually get that the left side is properly calculated, and left side is the probability of most likely sequence that ended in state I and generated symbols O1, O2, and ultimately OT plus 1. So this equation is really correct. And there is one more thing which I would like to know. What is really that j which maximizes this expression? So in order to determine that, I basically can write this one. P t plus 1 of I is equal So basically, if you compare this expression and this expression, they're the same. Max means find me the maximal value when we vary j. And argmax means find me for which j this value is maximized. In other words, what this really means? This really means find the most likely state, and that most likely state is denoted as pt plus 1 of I, that from which we transition to state I at time t plus 1. So this is time t plus 1, and this is the notation of the most likely state, which maximizes this expression. What is the most likely state from which we reach state I at time t plus 1? So that was iteration. And now we need to really determine the sequence, the most likely sequence. The most likely sequence, we will denote that most likely sequence as IT. The most likely sequence of transitions that led to the observed output. It's a sequence, right? And in fact, I'm going to use more precise notation. It would be I. And since it's a sequence I, it will consist of elements I1, I2, IT, T is basically in the index of a general element, and the last one would be IT, large T, in our case of course T is 6. So this is the most likely sequence of transitions. How I will calculate this most likely sequence? So at this moment my for loop will finish, right? For each t from 2 to big T minus 1, I will calculate delta and p's. After that, the for loop is finished. First I will calculate I large T. In fact, we've already seen this. What does this mean? I compare delta t of 1, delta t of 2, delta t of etc. And I'm trying to find which state has the highest probability delta. This is what I essentially did here. I am comparing delta 6, remember t is 6, delta 6 of 1 and delta 6 of 2. And I'm determining the most likely final state as the one which maximizes these probabilities. Here delta 6 of 2 is higher than delta 6 of 1. Therefore the index 2 corresponding to the state 2 maximizes the probability. Therefore the most likely state was the state 2, which was US. So this is just really to formalize that. Find most likely final state. And after I found them, I need to basically roll back and to find most likely states for t goes to t minus 1 down to 1. Observe now, I small t, the small t corresponds to this, I small t is p t plus 1 of I t plus 1. Why? What is p t plus 1 of I t plus 1? This is the most likely state that led to state t plus 1. So, what happens with t equal big T minus 1? If small t is equal big T minus 1, what we will get here? If t is equal t minus 1, what would happen? I t plus 1 will be equal of I t minus 1 plus 1, which would be I t. This is the most likely state at time t. So this would be the most likely state in time t. And then it, if t is equal to t minus 1, it would be I t minus 1, which would be the most likely state at time t minus 1. What is the most likely state at time t minus 1? Is the state that most likely led to state it in time t. We already know it. We determined it. Where? Here. What is the state that most likely led to state it? This is exactly a notation of that state. This is the state which from state at t minus 1 led to state at t. So basically this shows that this really works when t is equal t minus 1. And now when t is equal to t minus 2, we calculated what? We already know it and it minus 1. Since we know it and it minus 1, obviously I can calculate pt plus 1 of it plus 1. Why? Because p of t plus 1 will be p of large T minus 1, and it plus 1 will be I of t minus 1. These values on the right side are already calculated here. So basically all of this is feasible, and I will end up gradually filling the whole sequence I of the most likely states, time 1, 2, and finally t. I know it sounds like it sounds, but the algorithm is essentially very simple. And I believe it is relatively obvious why the algorithm works. It works because, in essence, this step is correct. That step correctly determines the most likely probability of the most likely sequence that led to the state I at time t plus 1. And this determines what is the most likely transition that led to that state. I calculated all of these probabilities, and then at the end I find out which one is the most likely state, and then I roll back using these probabilities here and ultimately determine the most likely states at times 1, 2, 3 till t minus 1. Let's try to give an example of how this really works. And stay with me, it requires some calculations, and if I mess up with calculations, I advise that basically you do all of this with me. Please. It will be much easier. So, In essence, if you look at the algorithm, I need to keep two sets of values, deltas and p's. I will write down again all the probabilities because I need them handy. This is my matrix A, consisting of A11, A12, A21, A22, which is this 05, 05, 03, 07. I need to copy my B's, B11, B12, B21, and B22. So B11, B12, B21, and B22. B11, B12, 01, 09. B21 and B22, 04 and 06, B21 and B22. My initial probabilities, pi of 1 is 1, pi of 2 is 0. And I need to reserve space to keep my deltas and pi's. So to do that, I will basically have two tables. This will be my table for deltas. So this would be my matrix delta, which will contain elements delta T of I, right? So I have here to have I, which can be 1 or 2, and I have here T for time, which can be 1, 2, 3, 4, 5, 6. Here I will place my deltas, and I need my matrix P and I will have my matrix P, which will contain the probabilities. These P's, right? These values P's. So I have one index for time and another index for state. Again, T can be from 1 to T, and state can go from 1 to N. And here, as we know, T is 6 times, and N is 2 states. So here I will start placing my P's. I have 2 rows for I, and I have 6 columns for T's. So this is the data that I need, and I now need to start executing the algorithm. So first I need to start, here is the algorithm. I need to start with initialization of the algorithm. Delta 1 of I is pi I times b I of O1. So, what is my O? Set of outputs. Set of outputs. Let's remember what was the set of outputs. Set of outputs was poor, poor, rich, rich, poor, rich. So obviously I need to use indices 1 and 2 because these probabilities B are in terms of indices 1 and 2. Remember, for B's, where is B here? This index for B's indicates the states, and 1 and 2 indicates rich and poor. So 1 is rich and 2 is poor. So basically outputs would be 2, 2, 1, 1, 2, 1. 2 being poor, 1 being rich. So this would be my O. So let's go back to the initialization. So I need to calculate delta 1 of 1. Remember, I goes from 1 to n, and n is 2. So I need to calculate delta 1 of 1 and delta 1 of 2. Let's replace. Here I is equal 1, so this is pi of 1 times b 1 of O1. And here would be pi of 2 times b2 of O1. In this case, believe it or not, life is actually easy. Pi of 1 is 1, pi of 2 is 0. b1 of O1 is there, b1 of O1. O1 is 2. b1 of 2 is 0.9. So this would be O1 is 2. So this would be 1 times b1 of 2. b1 of 2 is 0.9, b1 of 2, right? So this would be equal 0.9. Pi of 2 is 0. This doesn't matter, so this value would be 0. So this gives me delta 1 of 1 and delta 1 of 2. And I fill delta 1 of 1 and delta 1 of 2. They are here, 0.9 and 0.0. Delta 1 of 1 and delta 1 of 2. This completes the initialization step of the algorithm. And basically when you look at the algorithm, where is the algorithm? I forgot. This is the initialization step of the algorithm. So this completes the initialization of the step of the algorithm, calculating delta 1, 1 and delta 1, 2. And now I need to execute this iterative step of the algorithm. So I'm going to write down that iterative step again so that we will see it. Iterative steps of the algorithm. Iterative step of the algorithm is for t goes from 2 to t minus 1, delta t plus 1 of I is equal maximum by j delta t of j times AJI times BI of O t plus 1, where I goes from 1 to n, and pt plus 1 of I is equal argmax by j delta t of j times AJI, and again I should go from 1 to n. So this is the iterative step, goes from each t from 2 to t minus 1. So let's see how this step works for t equal 2. Say t is equal to, let's look at these expressions. In fact, I need to find maximum value of what? Delta t1 times a1I and delta t2 times a2I for each I. Why I'm looking for the maximum value of these two? Because the maximum value of this and this is in fact this maximum here. This is the maximum value of the product of delta tj times aj, because in our case j can be either 1 or 2. So I need to find this maximum value for each I, and I need to find argument. It is either I or it's either 1 or 2 that maximizes that value. So let's see what are these values. Say t is equal to, when I is equal 1, remember I need to calculate this max value for I1 and I2 because we have only two states. So when I is equal 1, I need to compare delta to 1 times A11. Observe, the second index corresponds to I. I need to compare this and delta 2 times A21. Observe again, this index corresponds to T. And this index, which is corresponds to to J, which I would like to find such that the whole value here is maximized. So I need to calculate this one and see which one is larger. Obviously I need to a little bit correct this, right? What is the correction I need to make? In this algorithm, t needs to start from 1 and not from 2. So, why? Because I need to calculate delta 2. So, t starts from 1, not from 2. Therefore, t would be 1 here and 1 here. T starts from 1. And I will correct that also in the original algorithm. So t starts from 1 and not from 2. Good. And now I can calculate this. Delta 1, 1 is what? 0.9. A11 is 0.5. Delta 1, 2 is 0. A21 is 0.3. So this result is 0.45. This result is 0. Which result is larger? Obviously this result is larger, which is obtained for j equal 1. Therefore, I can say that delta of t plus 1 of 1, right, is equal this maximum value, which is 0.45. This maximum value is 0.45 times bi of ot plus 1, which is b I is 1, b1 of O2. What is b1 of O2? O2 is again 2. b1 of 2 is 0.9. So b1 of, this is b1 of 2, which is 0.9, and the whole result is 0.45 times 0.9. And I will let you calculate that, which I will also try to do with my calculator. Stay tuned. 0.45 times 0.9. If I'm right, it gives 0.405. And since t was 1, delta of t plus 1 would be delta 2 of 1. Delta 2 of 1 is 0.405. This is delta 2 of 1. What is this? Pt plus 1 of I. This is essentially P2 of 1. And this is the index which maximizes this value. That index was 1. So P21 is equal 1. P21 is equal 1. Good. Now, of course, I need to recalculate for I equal 2. Remember, for each t, I need to find this value and this value, delta t plus 1 and pt plus 1, for each I. We just calculated for I1, and now I need to do same for I2. So for I2, the same story. I need to compare delta t is 1 times a 1 2. Now the second index indicates I2, and delta 1 2 times a 2 2. Why? Because this index indicates t, which was 1. This index will vary. It can be either 1 or 2. We will find for which j this value is larger. And this index here indicates I. So we need to calculate these two. Okay. Delta 1 1 is 0.9. A12 is 0.5. Delta 12 is 0. A22 is over 0.5, but obviously this value is larger. So I will maximize for j equal 1. And I, of course, need to calculate delta 2 of 2, where the second index indicates I now. Delta 2 2 will be like this, right? And this would be this product times, this is the maximum value of the product, right? times B2 of O2. Why B2 of O2? This is Bi of O2. B2 of O2, since O2 was 2, this is B2 2, and B2 2 is 0.6. And the product of these two was 0.27. So delta 2 will be 0.27, and this was achieved for j equal 1. So I will put 1 here for I equal 2 and for t equal 2. Oof! Now, as you would see very soon, life becomes more interesting. At this moment, I exhausted work for t equal 1, but now t needs to take 2 till big T minus 1, which is 5. So when t is equal 2, I again need to do the work for I equal 1 and for I equal 2. For I equal 1, I need to compare BT1 times A1 1 delta T1 times A1 1 and delta T2 times A2 1. Observe, this index corresponds to I. Observe, this index varies and corresponds to j, and this is my t. Similarly, for I equal 2, I need to compare delta t1 times a1 2 and delta t2 times a2 2. And then the index of the larger product will be essentially my p, which needs to go into this table. So let's do that step. Delta T1, since T is 2, is delta 2,1. Delta 2,1 is 0.405. Delta T2 is delta 22, delta 22, which is 0.27. A11, A21, A12, A22. A11, A21, A12, A22. A11, A21, A12, A22. 0.5, 0.3, 0.5, 0.7. Let me double check. A12 should be 0.5 and A21 0.3. And I should be able to read them from here. 0.5, 0.3, 0.3, 0.5, A22 was 0.7. was my mistake, didn't influence anything, but now does. So let's calculate all of this. 0.405 times 0.5. Zero 0.2025, and product of these two, 0.081. How about here? The result is the same, 0.2025, and here 0.189. So in both cases, for I equal 1 and I equal 2, the product is maximized for j equal 1. Therefore, in both cases, I put here once. And in order to calculate these two values, I need to see basically what would be bi of all three. So what is bi of all three? All three was the third output. The third output is now rich, which is 1. So this is B2 of 1, and this is B1 of 1. Why? Because here I is 1 and here I is 2. B11, what is B11? B11 0.1, and B21 is 0.4. 0.4, here is 0.1, and I need to multiply this with the maximum value of product to get delta t plus 1 of 1. So delta t plus 1 of 1 is the maximum value of the product. Maximum value of the product multiplied by B11, which is 0.1, and the result is 0.02025. And here I have the maximum value of the product. Multiplied by this, which would be 0.2025 times 0.4, which gives us 0.081. Ultimately, I need to put these two values in table. 0.02 and 0.081. So this completes the algorithm for t is equal 2. So now, of course, I need to do the same for t equal 3. And I know it's boring and annoying, and I advise you guys to skip all of this, but since I didn't calculate this before, I have to do this. So you can skip all the next steps till t equals 6 if you will, but unfortunately I can't because I didn't recalculate all of this. So again, I need to do this. I will copy all of that. I need to calculate what? Maximum between that and that. So that will be delta t of I. Delta t of 1 times A11, or delta t of 2 times A21, yes. On the other hand, delta t of 1 times A12, or delta t of 2 times A22. So I need to copy deltas. T is equal 3, and these deltas are just calculated. 002025 and 0.081, and I need to multiply with a's. We already had these a's. 0503 0507. I need to calculate these and to find maxima.